Welcome friends to my YouTube channel. Now in my previous lecture, I told about the temperature entropy diagram. Okay. Now in today's lecture, I shall going to discuss the change of entropy for various cases for gases. So first take the example of a perfect gas. So what happens in case of a perfect gas? Okay, so let's check. Now, from first law of thermodynamics, we can easily write the first law dq equals to du plus p dv. Okay. Now, if you substitute this by divide this by t, then what we get? Du by t plus p by t into dv. Now in case of a perfect gas, we can write PV equal to RT, and du, that we can write always CV dt, that is CV means molar specific heat at constant volume. So if we substitute that, then what we get? This is ds, and du means CV dt, that means CV dt by t, and p by t means r by v, so that is r into dv by v. Okay. So if you integrate this expression within the initial and final states, that means this is T1 to T2 and this is V1 to V2, then what we get? We get S2 minus S1, this equals to CV ln T2 by T1 plus R ln V2 by V1. Okay. So this is the general expression, one expression. Now this expression we can simplify it, that is this equation can be written in terms of Cp also. Okay, so how we can how we can make it to another form? Now we know for 1 mole perfect gas Cp minus Cv, this is equals to R. So you can put Cp minus Cv instead of R. So what we get? Cv ln T2 by T1 plus you put Cp minus Cv instead of R. So Cp ln V2 upon V1 minus Cv ln V2 upon V1. So what we get? We get Cp ln V2 by V1 plus Cv ln, this is simply T2 V1 by T1 V2. Okay, now from the Charles and Boyle combination formula, P1 V1 by T1 equals to P2 V2 by T2. So you can substitute it. Okay, so P1 V1 T2, this equals to P1 P2 V2 T1. So what will be my T2 V1? T2 V1 by T1 V2, this means P2 upon P1. So you can substitute it from Charles and Boyle's combination formula. Okay, so this is Cp ln V2 by V1, this is Cv ln, this means P2 by P1. Okay, so starting from this equation we arrive to another form by substituting Cp minus Cv instead of R. Now if you substitute Cp minus R instead of Cv, then you will get the another form. Okay, so you will get the another form. So I have to do it there. I don't erase these two equations because I need it. Okay, so if you substitute Cp minus R instead of Cv, so what we get? Cp ln T2 upon T1 minus R ln T2 by T1 plus R ln V2 by V1. Okay, so what we get? Cp ln T2 upon T1. Okay, so sorry, there will be, it will minus. Okay, so R ln, this is V2 T1 by V1 T2. So this is Cp ln T2 by T1 plus R ln, this is V2 T1 by V1 T2, that means P1 by P2. Okay, so these are the three different forms that I have calculated. Okay, so these three are the equations of entropy change for perfect gas. Okay, so let us check whether these equations are valid or not. Okay, so how we can check it? So if you simply take, okay, so if you simply take isothermal process, that means temperature remains constant. If you simply take the isothermal process, that means temperature remains constant. So what will be my change in entropy? At first find out where in which equation T is present, this. So this term becomes 0 since T1 T2 are equal. So this is R ln P1 upon P2, and they are also T, and this term is 0. So R ln V2 by V1. Okay, so this is perfect because in isothermal process Boyle's law holds good. You see, R ln P1 by P2, this is equal to R ln V2 by V1. That means P proportional to 1 by V. So this is fine. Now let us check for isobaric process, that is pressure remains constant. Okay, so in case of a isobaric process, what will be the change in entropy? Try to find out in which equation P is present, this equation. So this term is 0. So what we get? Cp ln T2 by T1, and this also 0. Okay, so Cp ln V2 by V1. This also correct because isobaric process pressure remains constant, and when pressure remains constant, we know Charles law, V is proportional to T. So that is T2 by T1, V2 by V1. Okay, so this is also agreed. Okay, now let us check in case of a isochoric process, what happens? V1 equals to V2. So what will be my S2 by S2 minus S1, or change in entropy? This term cancels, that is Cv ln P2 by P1, this equals to Cv ln T2 by T1, Cv ln T2 by T1. Okay, so this is also correct because when volume remains constant, pressure is proportional to T. So P2 by P1, T2 by T1. So you can see that we can easily express the change in entropy in terms of different thermodynamic variables, and we also find out the change in entropy for different cases, that is in thermodynamic processes, and it is agree with the natural expressions. Okay, that are natural expressions, so it is fine. So that is the change in entropy for a perfect gas. Now let us move towards ideal gas. So what happens in case of a ideal gas? Okay, so let us move. So let us check what happens for ideal gas. Okay, so dear guys, kindly take your pen and papers and note down it. Okay, also you can take a cup of coffee also. So uh, what happens in case of a real gas? Okay, what happens in case of a real gas? What happens in case of a real gas? Now we all know that this is the real gas equation for 1 mole real gas. This is the equation, van der Waal equation. Okay, this is the van der Waal equation for 1 mole real gas, and A is the force of attraction. A and B are van der Waal constant. This is due to the intermolecular force of attraction, and this is the volume correction term. Okay, now here we make a slight modification that we know that V is greater than A, so we can neglect this term. So we can neglect this term and there remains P. Okay, but we don't ignore B. If we ignore B, then it will become ideal gas equation, which we don't want. Okay, so we only ignore the higher order term, that is V square. Since V square is very much greater than A, so we can only ignore this term. So P into V minus V, this equals to R into T. So what will be my P upon T? My P upon T will be R by V minus V. Okay, so this is the case. Now just write down the first law of thermodynamics, dq, this equals to du plus pdv. Now divide it by T. Okay, what happens? Du means cv dt, that is cv into dt by T, plus p by T into dv. Okay, p by T into dv, this is simply ds, and this is cv dt upon T. And what is p by T? R into dv by v. So just do integral over initial and final states. So what we get? You will get this. So this is simply S2 minus S1. Okay, this is simply cv ln T2 upon T1. Okay, plus R ln, this is V2 minus B by V1 minus B. Okay, so this is the simple expression for change in entropy for real gas. Okay, this is the simple expression. So here we use the van der Waals equation, and by neglecting the V square term we simplify and get this result. So cv ln T2 by T2 plus R ln V2 minus B by V1 minus B. Since B term is involved here, that means this equation is valid for real gas only. Okay, now one thing I forgot to tell in my previous lectures, what is reversible and irreversible process? It's very important. What is reversible and irreversible processes? We talk about these two terms in many times, but I forgot to tell what is reversible and irreversible process. So let's try to find out what is reversible process. Okay, what is reversible? At first we talk about the reversible process. Okay, what is reversible process? Now a process is said to be reversible if the process can be retraced in the opposite direction. That means the working substance can perform the similar conditions as it does in the direct process. Okay, so that can be retraced in the opposite direction. Okay, so that the working substance undergoes exactly the same conditions as it does in the forward process. So let us try to understand this by taking a suitable example, then the concept will be clear. So let's take an example. So you take PV diagram, the best simple example, you take the Carnot cycle. You will understand it from this. Okay, so we draw in Carnot cycle that the two successive expansions and compressions. Okay, two successive expansions and compressions, that is along AB there is a isothermal expansion, and along CD there is a isothermal compression. Along BC there is a adiabatic expansion, and along DA there is a adiabatic compression. So just see the picture. In adiabatic expansion, the heat which was absorbed from source, in adiabatic compression the heat is rejected to sink, and that can be retraced in the opposite direction. Okay, similarly you can say in adiabatic expansion work is done by the gas, and in in isothermal expansion work is done by the gas, and in isothermal compression work is done on the gas. So you see that in direct process and in reverse process they are both exist. Okay, along AB isothermal expansion, heat is absorbed from source, and along CD isothermal compression, heat is rejected to sink. Along isothermal expansion, work is done by the gas, and along isothermal compression, work is done on the gas. Okay, so similarly along BC there is a adiabatic compression, the temperature adiabatic expansion, the temperature falls down, and along DA adiabatic compression, temperature rises. So this is a suitable example of reversible process. That means you can say all isothermal and adiabatic processes are reversible. They are all reversible when they are performed slowly. When performed slowly. Okay. When performed slowly. So this is one example. Another example you can take: when ice melts into water, heat is absorbed by it, and similarly when water converted to ice, the same amount of heat is rejected by it. So when ice melts into water, heat is absorbed by it, and when water is converted to ice, the similar amount of heat is rejected by it. Okay. Melting of ice and vice versa. Melting of ice and vice versa. So this is also an example. Okay, so all isothermal and adiabatic processes are reversible when they are performed slowly. This we took as an example, and we also took the conversion of ice into water and the vice versa. Okay, so these processes can be retraced in the opposite direction. Okay, now there are two conditions for a process to be reversible that I have to mention. First of all, there I see that slowly, that means this process must be slow. Okay, can be performed slowly, can be performed slowly, that is nearly quasi-static, nearly quasi-static. Quasi-static, what does it mean? Quasi means nearly and static means equilibrium. That means nearly in equilibrium, each stage is almost in equilibrium with one another. Okay, so this process can be performed very slowly. That means it is a quasi-static process. Quasi means nearly and static means equilibrium. So all the stages or steps are in equilibrium, almost in equilibrium. Okay, and another thing that should be satisfied, that no frictional force will be present. Okay, no frictional force, no frictional force is present. Okay, so this is what about reversible process. Okay, so let us move to an irreversible process. What do we usually mean by irreversible process? This is simple because all the naturally occurring processes are irreversible, so you all know it. Okay, all natural processes occurring in nature are irreversible, so you are familiar with this term. What is irreversible process? That we all know. Okay, what is irreversible? The marker is working slowly, I have to bring a new one. Okay, so irreversible, what is that? Simply the opposite. This process cannot be retraced in opposite direction. Okay, cannot be retraced in the opposite direction, that is called irreversible process. And all the naturally occurring phenomena are processes are irreversible process, and entropy increases in irreversible process. So as a result, the entropy of the universe is also increasing, that I told in the law of increase of entropy or principle of increase of entropy. Now if you take suitable example, just you take Joule Kelvin effect or Joule Thomson effect, JT process, we will study it later, that there are successive tubes, porous plugs through which gas is passed under the flow of a huge pressure difference. Okay, so if the direction of the gas flow is made opposite, then the similar phenomena cannot be observed. we pass a gas through successive porous plugs or tubes, okay, and observed how much amount of heating or cooling is produced. But if we change the direction of flow of gas, the similar phenomena cannot be observed. So JT process is an irreversible process, Joule-Thomson process. Another example you take, when current flows through a resistance, okay, heat is produced, that is I square RT. But if we make the direction of current reverse, this phenomena cannot be observed. So this is also an irreversible process. Okay, Joule-Thomson process, on reversal of the flow of gas, similar amount of heating or cooling cannot be produced. Or if we change the direction of current, then similar amount of heating that can be produced in the direct process cannot be observed. So current flows through a resistance is a irreversible Joule heat loss. So these are the examples. Okay, and another example you can take, rubbing your hands when heat is produced. Okay, rubbing hands, this is also a simple example, rubbing of hands. Okay, or you can say the deformation of plastic, these are the irreversible process. Deformation of plastic, so these are the irreversible processes, okay, that cannot be retraced in the opposite direction. So dear guys, if you don't subscribe my channel, then kindly subscribe it and share it to your friends to get the latest updated videos. Okay, thank you.